Welcome to this fascinating problem involving a particle under an inverse square force. We have a tiny 10-gram particle, initially at rest at the 1 meter mark on the positive x-axis. The force acting on it is attractive and goes like negative k over 2x squared, always pulling it toward the origin. Let's identify what we're given. The mass is 10 to the negative 2 kilograms. That's just 10 grams. The force constant k equals 10 to the negative 2. Newton meters squared. At time t equals 0, the particle sits at x equals 1 meter with 0 initial velocity. We need to find the velocity when it reaches x equals 0.5 meters, and the time when it reaches x equals 0.25 meters. Because this force depends only on position, it's conservative. We can define a potential energy function by integrating the force. V of x equals negative integral of f dx, which gives us negative k over 2x. This potential energy well gets deeper as we move closer to the origin. Now here's the key insight. Total mechanical energy is conserved. At the starting point, x equals 1 meter with v equals 0. The total energy is just the potential energy. E equals v of 1, which is negative k over 2. As the particle moves to any position x, this energy stays constant. Let's solve for velocity. Setting up the energy equation at position x, 1/2 mv squared plus v of x equals e. Substituting v of x equals negative k over 2lx and e equals negative k over 2. Then solving for v, we get v squared equals k over m times the quantity 1 over x minus 1. Taking the square root gives us the velocity formula. Now let's calculate the velocity at x equals 0.5 meters. We substitute into our formula, v equals the square root of k over m times the quantity 1 over 0.5 minus 1. Since k and m are both 10 to the negative 2, their ratio is exactly 1. And 1 over 0.5 is 2, so 2 minus 1 equals 1. The square root of 1 times 1 is simply 1. So the velocity at x equals 0.5 meters is exactly 1 meter per second. For part B, we need the time to reach x equals 0.25 meters. Here's where it gets interesting. Since v equals dx over dt, we can write dt equals dx over v. Substituting our velocity formula and integrating from x equals 1 to x equals 0.25 gives us the total time. This integral requires a trigonometric substitution. Using x equals sine squared theta transforms it nicely. After working through the calculus, we get t equals 1 over square root of k over m times the quantity pi over 3 plus square root of 3 over 4. Since k over m equals 1 in our problem, this simplifies to approximately 1.48 seconds. Let's watch the complete motion. The particle starts at 1 meter, passes through 0.5 meters at 1 meter per second, and continues accelerating as the force grows stronger. Notice how the force arrow gets longer as we approach the origin. At 1:48 seconds, we reach our final target at x equals 0.25 meters. Let's summarize our results. For part A, using energy conservation, we found that the velocity at x equals 0.5 meters is exactly 1 meter per second, directed toward the origin. For part B, using the time integral with a trigonometric substitution, we found the time to reach x equals 0.25 meters is approximately 1.48 seconds. The beautiful simplicity of these answers comes from the fact that k over m equals 1 in this problem.